Hello everyone. We are in our third lecture on redox chemistry. So far we have discussed in our last class the Nernst equation from the thermodynamic approach. Now this same Nernst equation will be discussed from the context of the equilibrium constant and the reaction isotherm concept. The reaction isotherm is actually the Van 't Hoff equation, which is also known as the reaction isotherm. So this is the equation which is actually delta Z equals to delta Z0 plus RT ln Ka dash. So delta G is the free energy change of the reaction, of the redox reaction. Delta G0 is the same thing but at STP, under the standard temperature and pressure. It is the temperature of the reaction and R is the universal gas constant, while Ka dash is the ratio of the activity of the products and the reactants. That means this ratio is the ratio of their activities at any time or at any instance of the reaction. Not only at the time of equilibrium, but at any time. So when the reaction goes to equilibrium, then this Ka dash becomes Ka. That means it becomes actually the equilibrium constant. Now delta G0 has the expression minus RT ln Ka from the thermodynamics previous chapters, as you have learned from your previous semesters, that delta Z0 is minus RT ln Ka, while Ka is the equilibrium constant in terms of activity, and actually the terminology is activity equilibrium constant. So this delta G0 is minus RT ln Ka. Okay, so at equilibrium, this delta G becomes 0 and delta Z0 becomes minus RT ln Ka. This dash is removed. That means dash is removed means this Ka becomes the activity ratio of the products and the reactants at the time of equilibrium. Okay, so this is elaborated here. Ka dash, product concentration or activity at any time, divided by reactant concentration at any time, concentration or activity at any time, while Ka means product concentration or activity at equilibrium divided by reactant concentration or activity at equilibrium. Now at equilibrium, delta G equal to 0, as I have said earlier, and if delta G becomes 0, then this right hand side part will also become 0. As a result, delta Z0 would become minus RT ln K dash. This dash now can be removed because this K dash becomes now the equilibrium constant in terms of activity. So K dash represents the ratio of the activities of the products and reactants at equilibrium. Hence it becomes the ratio of activity at equilibrium. That means Ka dash is now the activity equilibrium constant. As a result, K dash becomes Ka. So this K dash can now be written as Ka. Okay, previously it was Ka dash, but since the reaction is at the condition of equilibrium, so you can write K dash as Ka. So the final expression of delta Z0 is minus RT ln Ka. Now the chemical equilibrium, Van 't Hoff equation for chemical equilibrium. This is the Van 't Hoff equation or the reaction isotherm. Now we have to approach towards the Nernst equation. So in our previous class we have learned that delta Z equal to minus NFE, and if it is at a standard state, then delta G becomes delta Z0 and E becomes E0. That means delta G0 becomes minus NFE0. So we have to put these values. Instead of delta G we have to write minus NFE, and instead of delta Z0 we have to write minus NFE0. So we put these values here. As a result, we get E equals to E0 plus RT by NF ln 1 by Ka dash. Why it is 1 by K dash? Because there is minus negative term. So if this negative term is removed, then this would become this positive sign would become the negative sign. Now, in order to make this negative sign into positive sign, we have to reciprocate K dash, and as a result, it is written as 1 by K dash. Now, this K dash is the activity ratio of the products and the reactants. Now, if activity is replaced by concentration term, then Ka dash becomes Kc dash. So here K dash has been replaced by Kc dash. So the equation becomes E equals to E0 plus RT by NF ln 1 by Kc dash. Now we recap the equation, the reduction equation. The metal cation plus electron equal to the neutral metal. Now for this reduction equation, the ratio of the concentration of the product over the reactants, that is the active mass of the product and the reactant, can be written as active mass of M over active mass of the metal cation. So if Kc dash is replaced by this term, active mass of the metal over the active mass of the metal cation, then here 1 over concentration of M by concentration of M dash. That means it is actually concentration of M cation divided by concentration of M. So 1 by Kc dash is written as this one. Finally, M is the concentration of the metal, which is actually the solid, and we know that in case of solid and liquid, this term is actually unity. That means this term is 1, so this becomes ln M cation, metal cation concentration. So we have got equation 2, which is another form of the Nernst equation for this particular reaction, which is E equals to E0 plus RT by NF ln M cation concentration. Okay, so as I have already said that in different books you can see different conventions of writing this equation. Here in some books the negative sign is written. In that case here 1 by metal cation concentration is written. Okay, or sometimes it is negative sign and this is as it is. So in those cases the reverse reaction is used. That means metal reversible sign metal cation. That means the oxidation reaction is used. So if you write oxidation reaction in terms of instead of this equation, then you have to put a negative sign here. So do not get confused on different conventions adopted by different books or authors. Only stick onto the IUPAC recommended convention. So we have to always write the reduction reaction, and for that we have to always put a positive sign here. Okay, so if you if you want to replace the concentration term into activity, then equation 2 can be written as equation 3, which is E equals to E0 plus RT by NF ln activity of metal cation. So this is equation 3. So we have different forms of the Nernst equation as in the previous slide. In equation 1 it was E equals to E0 plus RT by NF A ln A. Okay, simple. That was the simple presentation of the Nernst equation. But in the equation 2, from the context of this reduction reaction, we can write this equation. And equation 3 is similar to equation 1. Instead of A, we are just writing here the active mass of the metal cation. So these are the different forms of the Nernst equation. And also Nernst equation can be written as the concentration of the oxidant as well as the concentration of the reductant, we are showing you how. Look, here oxidant plus electron or electrons equal to the reductant. So this is the reaction presentation. So in equation 4 you can write like this. You can represent the Nernst equation like this: E equals to E0 plus RT by NF ln oxidant concentration over reductant concentration. Okay, here oxidant means the metal cation. So metal cation in the numerator and normal metal in the denominator. Okay. So what about the description of the other parameters? Like F is the Faraday, T is the temperature, standard temperature, 298.15 Kelvin, R is the universal gas constant. So let us put these values here, and instead of R we have put here the SI unit 8.314, the temperature, and natural log has been converted into 10 base log base 10. So 2.303 has been multiplied here, and the Faraday value 96,485 has been put in this denominator. So overall result of this multiplication and division is 0.0591, and N is in the denominator. So this is the fifth equation of the Nernst equation, which is actually used in the STP. Okay, so E equals to E0 plus 0.0591 by N log oxidant concentration by reductant concentration for this form of the equation. And this equation 5 is the most widely used equation. This equation will be used vigorously in this chapter. So that's all for today. We shall discuss the different examples in our next class. Okay, and find out the equilibrium constant and other parameters. So that's all for today. Have a nice day. Thank you.